Okay, so my presentation will be rather short compared to other talks. My name is Dmitriy, and I will present our preliminary experiments with using machine learning for segmentation of zigzag patterns on the micrographs of bovine serum albumin films. So first of all, what are these films? They are the residue left on the surface after the evaporation of biopolymer solution, which we presume is formed by crystal hydrates of biopolymers. Usually, when a droplet of biological fluid or biopolymer solution is dried, it forms various structures and textures on the substrate. For example, like this, and these textures, well, the visual look of these textures can depend on many factors, including the state of the biopolymer and its interaction with other components in the solution, which makes such films a promising area for low-cost diagnostics. In our experiments, we were using model systems like saline solutions of DNA or BSA dried under specific conditions. And we were studying how the resulting textures change when the solution is subjected to a physical factor or when biological active substance is added to the solution. We observed that the presence of DNA or BSA produces specific kind of patterns, which we call zigzags, and they are absent if there is no protein, or if the protein is if the protein structure is significantly disrupted by some kind of influence. These patterns seem to follow the model of crystallization under strong anisotropy in a thin layer, which was theoretically modeled by Raz and other authors. In this model, the growing structure reaches the boundary, then reflects and branches out, and in this way, such kind of zigzag or hexagonal patterns are created. To numerically characterize these textures, we were using the density of zigzag segments manually marked on each micrograph of the films. However, this process is time-consuming and subjective, especially in ambiguous cases. So this can be a major obstacle in large-scale research and diagnostics which need to be performed quickly. So to our previous attempt to automate this process was using an algorithmic approach that relied on zigzags geometric structures. It worked well when the images contained clear zigzags without which dominated the image, but in cases when the photographs were noisy, blurry, or contained other types of textures, this approach performed poorly. So we were looking for alternative and more flexible solutions. Since then, machine learning has proved to be quite a good choice for many scientific tasks. And comparing to classical methods, which are well understood but require intricate tuning and often fail on complex images, neural networks, which is modern popular version of machine learning, are universal function approximators that can be hard to interpret, but can learn complex patterns from a large set of examples. They were originally created as a digital analog of brain connectome, which sums up incoming signals, transforms them in via nonlinear function, and transfer this signal further. Nowadays, they are often viewed as cascades of trainable signal processing filters, or as nonlinear transformations of state space, which geometrically represent the relations in the data. Such models are trained using an optimization process, which is usually a gradient descent. And in this way, the weights of this network are gradually changed to reduce the prediction error. Usually, for image analysis, networks of the convolutional neural network type are employed, which can recognize a hierarchy of increasingly complex features. And this is especially useful for tasks where certain patterns can be clearly visible in the data, but are hard to describe mathematically. In our case, we were dealing with the task of segmentation, which requires not only to detect if the object is present in the image, but also to determine which pixels belong to it. A classical architecture for such tasks is UNet, which consists of encoder, which extracts essential features and compresses them into lengthy representation, decoder, which constructs segmentation masks from this representation, and discrete connections, which preserve fine details which are lost during compression. We trained our model on a data set of 50,000 patches of 64 by 64 pixels, which were randomly cropped and transformed. And to create final segmentation masks, we split our images into tiles and then stitched the predictions together. So the overall results are like this. For the overall perfume density of zigzag segmentations, we observe about 90% correlation between the neural network predictions and the manual markings. So at least in a statistical sense, these predictions can be used for rough initial estimates of zigzag density and to determine the threshold of an influence factor at which zigzags formation of zigzags begins to be significantly affected. However, at the level of individual photos, there is a different picture because it seems that good match tends to be between model predictions and manual markings when the zigzag structures are clearly visible in the micrographs. And in the rest of the cases, the predictions do not really overlap between each other. This might not necessarily mean that model predictions are inferior, because manual markings can be subject to human error and inconsistencies, but visual inspection indicates that the model indeed in some cases fails to detect zigzags or interprets other types of texture as zigzag patterns. We suspect this may be due to a number of potential causes, from imbalanced and inconsistent data to insufficient visual context, or even to a wrong choice of training setup. What is actually the case and how to improve the results remains to be seen, but we hope to find the answers and to expand upon our analysis beyond just segmentation in the future work. So that's all. Thank you for the attention. Any questions?
Thank you very much, Dmytro. I would like to ask first to the people in presence in the room if they have any question.
Are there any questions? At the moment, no questions. So, yes, I'm sorry, there is a question. Professor Granyuk. Sorry, and how do you take into account the specifics of DNA?
It's not
in this
very good
picture?
the microphone. Sorry, it's very difficult for us to understand.
We move to another microphone.
Thank you very much.
Sorry, once more. How do you take into account the specific features of the DNA molecules in your pictures? Because we can observe similar pictures in other situations. Thank you.
I'm sorry, can you clarify what do you mean by specific features of DNA on this? I do not understand what is actually.
Maybe you can say the type of DNA, calf thymus or something, chicken DNA.
I see.
Like this, and also maybe proteins.
Yeah,
Yes.
unfortunately, we did not have the opportunity to test this with different types of DNA. We are using sigma DNA, I think, but the sigma Aldrich was not producing this kind of patterns. We suspect because it had lower quality than sigma. So we switched to bovine serum albumin as a more reliable alternative. But yeah, well, at least for some sort of DNA, we were observing this kind of patterns.
Thank you, Dmitry. You answered. Thank you. So, other questions in the conference room? No questions. So, Francesca, we can.
I ask if you have a question in the Zoom room, please raise your hand. In the while, I have some question myself. Thank you very much, Dmitriy, for your interesting work. And I would like to ask you if when you divide your image in segment, how do you decide the size? Yes, here. How do you decide the size of the segment, and does your result depends on the size of the segment?
Because we trained on a data set of 64 by 64 pixels, we also divide into 64 by 64 pixels. Well, actually, this illustration is a simplification because actually in our script, we create multiple shifting grids and average out their predictions. So we kind of use a sliding window and average the results. But here it's 64 by 64 pixels for illustration. Did I answer your question?
Maybe, but I'm not sure, so I will follow up. So is it important the number of nodes or angles that you have in each segment? Is there any requirement beside the pixel to in the segmentation mask, or it doesn't matter?
For our basic analysis, we only care about the density of these patterns, but the geometric parameters of these zigzag structures can also be relevant in some contexts. For example, we observed that the lengths of the segments may depend on the concentration of sodium, but otherwise we didn't find that it was particularly informative. So we usually analyze just the total number of these patterns.
Thank you very much. And then I have a curiosity about what you wrote in the acknowledgement. So I see that you use Claude and Gemini and you didn't use ChatGPT for the imaging. Is there a reason?
Well, the main reason is that Gemini image generator is better and allows more uses in the free version. And well, also I used some some images were generated not as AI image generation, but as they helped me create code to produce this kind of illustrations. And well, I didn't use ChatGPT mostly because these other tools were enough, so I didn't bother to use ChatGPT.
Okay, because lately there has been a big shift from ChatGPT to Claude because of ethical reason, and I was wondering if there was something else behind the technically also. So thank you very much, Dmytro. If there is not any other